In this video, we'll continue to look at the properties of convergent series, and we'll introduce a new notion, absolute convergence, which we'll find to be useful in studying the convergence of infinite series. Let me start by giving you the definition of absolute convergence. So a series that is the sum of ak with k going from 1 to infinity is said to be absolutely convergent if the series obtained by taking the absolute value of each term, by which I mean the series, which is the sum of the absolute value of ak with k going from 1 to infinity. Now we have taken the absolute value of each term. If this series converges, that is when we say that our original series, the sum of ak, was absolutely convergent. And the good thing about this notion of absolute convergence is that if a series, and that is a statement, that is a fact that I want us to have, I won't be able to prove this in this module, but I want us to have this important fact that if a series, if the sum of ak with k going from 1 to infinity is absolutely convergent, then it is also convergent. So absolute convergence implies convergence, and that is a good thing. Now, to see how absolute convergence can be established, so this is something we might want to establish, so we have a proof for the convergence of our sequence that we are interested in, is a new test which we'll call comparison test. And it is based on the idea, as you could probably guess from the name, of comparing our original sequence, well, rather this one that we obtain from it, to a sequence that we know something about. So let me state the theorem. So let this sequence, the sum of ck with k going from 1 to infinity, be a convergent series of non-negative numbers ck. So we are assuming two things: that this infinite series is convergent, and that each of these terms in the series are non-negative. Okay, so this holds true for all k. Okay, and assume that the absolute value of each term in our original series is less than or equal to ck. And this again holds for all terms, for all indices k. Okay, our statement is that then the infinite series, that is the sum of ak with k going from 1 to infinity, is absolutely convergent. Okay, so what we have here is we are interested in this series and we want to establish that it is absolutely convergent. What we have in this comparison test is another series, which is a comparison series, which is used for comparison, for which we know that it converges with non-negative entries, and that each term in that comparison series is greater than or equal to the absolute values of each term in our original series. So let's prove this. So what we'll need for absolute convergence, by definition, is we want to prove that this series converges. That is by definition our aim. So by definition, we have to look at the nth partial sum of this series and see that it converges to some number. Well, let's look at the nth partial sum, and what we can immediately do is to give it an upper bound by taking each term and replacing it by the corresponding term in our comparison series. By this estimation upper bound, we get the nth partial sum of our comparison series, which we know to be convergent. So this tends to some number c that is a finite number as we take n to infinity. So what we can definitely say is that hence the sequence of partial sums which are the sum of the absolute value of ak going with k going from 1 to n is bounded above by this number, the sum of our comparison series, so by capital C, and it is also increasing. Why? Because in each new term in the sequence of partial sums, we are going to add another number that is non-negative, because we are adding new terms as the absolute values of terms in our original sequence. Taking absolute values means we are adding non-negative numbers, increasing the sequence each time we do that. So it is both bounded above and it is increasing. So both bounded above and increasing by the monotone convergence theorem. This sequence of partial sums being bounded above and increasing has to converge. Okay, so by the monotone convergence theorem, the sequence of partial sums converges as n goes to infinity. And that is exactly the definition of absolute convergence for our original series. That is the sum of ak with k going from 1 to infinity. And we have concluded the proof. Okay, so this is the end of our proof. We have established that AK, the series, the sum of AK, is absolutely convergent. And now let's consider an example in which this comparison sequence is useful and the comparison test can be applied. Example, I want you to consider the sum of sine of k divided by 2 to the power k, with k going from 0 to infinity. Of course, the k equals 0 gives us 0, so it doesn't really matter which of these numbers I'm starting from. So what I would like you to do is to pause the video and think about this series, how the comparison test could be applied to proving that this series is absolutely convergent and hence convergent. Pause the video and think about it. Okay, I hope you paused it and have found that if we want to establish the absolute convergence of this series, we have to look at this series, which is taking the absolute value of each term and adding those up. But of course, we can give a comparison sequence for this series, a comparison series for this series, which is just 1 over 2 to the power k summed up, because the sine of k in absolute value is less than 1, less than or equal to 1. It's the sine function oscillates between -1 and 1, so we can definitely take this series to be a comparison series. But of course, this is nothing but the geometric series with q being equal to a half, with quotient equal to a half. So this is just the geometric series formula that we have obtained previously, that we can apply here, and we get, of course, 2. So we get the sum 2. So what we have seen, that this is a comparison series which have non-negative entries, and it's convergent. It has a definite limit, a finite limit, and each term is an upper bound for each term in the original series in absolute value. Okay, I hope you got it right, and I'll see you in the next one.